Hi there everybody and welcome back to chemistry. My name is Jeremy Krug. In this video we're learning a somewhat more advanced topic with regard to chemical reactions, and this is predicting products of reactions. Now, in order to accompany this video, I have a free list of prediction rules that I have down in the description below. So go ahead and download that and use that to follow along and work through these examples as we do them. If you're new here, welcome aboard. I'd like to welcome you to my channel. This is the place for all things honors chemistry and AP chemistry. Check out the playlist. That's where the action is. Hope you like what you see. If you do, please consider subscribing to my channel. That way you won't miss a thing. Now, as we jump right into the concept of predicting products of reactions, we're going to start with the first example. Here we have Mg, which is magnesium, plus O2, which is oxygen gas. Now, these first few reactions that we're going to predict are going to be synthesis processes. Now, a very common rule for a reaction like this is this rule right here. A metal and a nonmetal combine to form an ionic compound. So basically what's going to happen here is these two elements are going to combine to make magnesium oxide, MgO. Now, whenever you write that formula, make sure that you're writing the ionic compound correctly. Use your ions, your ion chart, your periodic table, whatever you need in order to write this correctly. We know that Mg, magnesium, has a charge of positive 2, and oxide, O, has a charge of negative 2. So they cancel out, and that's why it's MgO as our product. Let's take a look at another example here. We have Ca plus S, calcium plus sulfur. Now, this is very similar to the last one that we did here. A metal and a nonmetal combine to form an ionic compound. So once again, the calcium and the sulfur are just going to get together to make calcium sulfide, just like this. And those charges do cancel out on those respective ions. We know that calcium is positive 2 according to the periodic table because it's in group 2, and sulfide is negative 2 because it's in group 16. So plus 2 minus 2, those cancel out. So CAS is our answer. Let's try this example here. Li2O plus H2O. Now this is a somewhat more complex example. There's a different rule we're going to use for this. A metallic oxide combines with water to give a metallic hydroxide. Now hopefully you see that Li2O qualifies as a metallic oxide because lithium is a metal and there's oxygen after it, so that's a metallic oxide. And of course, H2O is water. So the product is a metallic hydroxide. Our metal here, of course, is lithium, so the formula is going to be LiOH, our lithium hydroxide. Now, as you look at this equation, you might notice that this is not a balanced equation. And you can balance this if you want to. I'm not going to stop you from balancing that. In these examples, I'm not going to balance them. And the reason is that it's possible that you get the wrong answer. And if you get the wrong answer, then you're going to have an equation that is unbalanceable. And I don't want you to waste your time on that. So that's why in my classes anyway, I just tell students if we're balancing equations, balance equations. If we're predicting products, focus on the prediction of the products. Of course, if you did this correctly, it would be very easy to balance. All you would need is a 2 in front of that lithium hydroxide to balance this. And let's try another one here. Let's try this equation, CO2 plus H2O. Now this is a somewhat different example as well, but notice that carbon is not a metal. This is a nonmetal. So in this case, we don't have a metallic oxide plus water. We have a non-metallic oxide plus water. And the rule for that is a non-metallic oxide combines with water to produce an acid. Now, we've learned earlier in this course that an acid, in its most simple definition, essentially starts with hydrogen. So we're going to put H on the front there and H2CO3. Now, I'll be honest with you. Sometimes it's not easy to predict the formula of the acid. Sometimes you just have to know what it is. In this case, though, I've tried to make it simple. The number of atoms on the left side add up to the number of atoms on the right side. So we just combine this, H2CO3. So at this level, I'm going to try to make the questions fairly simple and straightforward. So H2CO3 is our acid. That's an acid called carbonic acid, which is found in carbonated beverages, sometimes called carbonated water. All right, let's take a look at another example. Now here we can see we're not dealing with a synthesis reaction anymore. This is a decomposition reaction. And of course we can identify it as decomposition because it has one reactant. Any equation, any reaction that has just one reactant has to be decomposition. And whenever we have an ionic compound with two elements, these are going to decompose into their respective elements. And so the products are going to be Ag, which is silver metal, and O2, which is oxygen gas. And it's O2 because oxygen is one of those 7 diatomic elements that we learned about earlier in the course whenever we were learning about the periodic table. So these are the products, Ag plus O2. Now, of course, you can look at that and see, hey, this is not a balanced equation. And if you want to, you're welcome to go ahead and balance that by balancing the oxygens by putting a 2 right here, and then balancing the silvers by putting a 4 right there. But once again, simple to do. But on this type of example, I'm not going to worry too much about balancing. Of course, you can do that on your own if you want. Let's try another one. NiCO3. Now this is not the same type of example as we had in the last example because this is not a simple ionic compound containing 2 elements. We have 3 elements, nickel, carbon, and oxygen. The rule for something like this is that when a metallic carbonate is heated, and that's what this is because nickel is a metal and CO3 is the carbonate ion, it says it's going to decompose to form CO2, carbon dioxide gas, and a metallic oxide. So, of course, CO2 is one of the products, and the metallic oxide would be nickel oxide. And since nickel has a positive 2 charge on the reactant side of this reaction, it's safe to assume that nickel is also going to have a positive 2 charge on the product side of this reaction. So that's why I can write it as NiO, because O is a -2 and Ni is a +2. So there we have our products for this reaction. So that's a metallic carbonate that produces CO2 and a metallic oxide. Let's try another example. Let's try NaClO3. Now ClO3 is the chlorate polyatomic ion. So here we have a metallic chlorate. And the rule for those decompositions looks like this. When a metallic chlorate is heated, it decomposes to form a metallic chloride and O2. So chloride just means it ends with Cl. So the metallic chloride in this case would be sodium chloride, NaCl. And of course, O2, oxygen gas, is the other product. And of course, if you want to, you could balance that fairly easily as well. Now, let's jump right into the next example here, NaOH. So this is a metallic hydroxide. Now, how does that work? Well, the rule for this is that when some, and this doesn't happen with all of them, but some of them it does, when some metallic hydroxides are heated, they decompose to form a metallic oxide and water. So what's the metal in that metallic oxide going to be? Well, the only metal here is sodium. So it's going to be sodium oxide. And you might remember that sodium has a +1 charge and oxide has a -2 charge. That's why we swap the charges and it's written as Na2O, just like this. And of course, water is H2O. So there we have our equation. This is not a balanced equation, but you could balance it fairly simply by just sticking a coefficient of 2 out here in front of the sodium hydroxide. Let's try another example with a decomposition process, H2SO3. Now you might remember the last example was a metallic hydroxide. This one is an acid. And some acids can decompose to form a non-metallic oxide and water. So we know that H2O is one of the products, and the non-metal in here, of course, is sulfur. So this is going to be a sulfur oxide. Now, just like I said earlier, whenever we were forming acids, sometimes you just have to know what that non-metallic oxide is going to be. In these examples that I give you in this course, I'm going to try to keep it pretty simple. So notice that just like we had before, the number of atoms on the left side add up to the same as the number of atoms on the right side. So it's SO2, sulfur dioxide, and water. And that doesn't always work out as nicely as that, where you have 3 oxygens on the left and 3 oxygens on the right, and 1 sulfur on the left and 1 sulfur on the right. But for these, I'm going to try to keep it fairly simple. So those are some decomposition reactions. Let's jump right into single replacement. Now, let's say we have this mixture right here. Gold, which is Au, being reacted with KNO3, potassium nitrate. Now, for single replacement reactions, we need to realize that there is a hierarchy that we're going to use. This is something called an activity series. And that's why this rule is written here. An active metal will replace a less active metallic ion in a compound, and a less active metal will not replace a more active metallic ion in a compound. Now, what in the world does that mean? Well, as you look here at this equation, Au, gold, is trying to kick out K, which is potassium. So we have to look at the hierarchy, the activity series of the metals. Now, here is a list of the activity series for a lot of the metals that we use in these reactions. Now, notice where gold is. Gold Au is at the very bottom of that pecking order, very bottom of that list. Where is K? Where's potassium? Do you see it? It's almost at the very top. It's right up here. And so if you're thinking about this, can gold kick out potassium? Well, it can't. Gold is lower than potassium on this hierarchy, on this activity series. So the answer for this reaction is, well, no reaction, because gold cannot kick out potassium. This is kind of like, for example, here I am in the school, I'm in my classroom, gold, and if I were to march myself into the principal's office up here and say to the principal, "You're fired," would that work? No. I cannot fire the principal. I am way down here at the bottom of this totem pole, and the principal's way up here pretty close to the top. But what if it went in the other direction? What if the principal came into my classroom and said, "You're fired, Mr. Krug"? Well, then I'd be fired, right? The principal up here can kick me out, but I can't kick him out. And so there's one direction here for this hierarchy. So gold cannot kick out potassium, so this is a no reaction. Now let's try another example. Let's try this mixture right here. Zinc, Zn, plus AgNO3. So once again, we're looking at those rules. Zinc versus silver. Where is zinc on this activity series? Well, zinc is pretty close to the middle. It's right here. And silver is way down here at the bottom. So do you think zinc can kick out silver? Absolutely. Zinc is higher than silver on the activity series. So which element gets kicked out and is all by itself? Well, Ag gets kicked out. And so zinc is going to get with nitrate. So Ag is by itself, and then zinc pairs with the nitrate ion. Now we have to think about the charges. Zinc is a +2. You can see that on your ion chart. And then NO3, the nitrate ion, has a -1 charge. So +2 and -1, we have to swap those charges. And so that's why we have a 2 and parentheses around this. So that's your set of products for this reaction. Zn, parentheses NO3, close parentheses 2, and silver metal, Ag. Now let's take a look at another example, copper plus water. So once again, we can take a look at the activity series and we can see where copper is. So here's copper right here, kind of fairly close to the bottom, and it's trying to kick out hydrogen from the water. And hydrogen is a little bit above copper, isn't it? So is this going to work? Can copper kick out hydrogen? It cannot. It is too low on that activity series. So what's the answer? No reaction, isn't it? And you've probably experienced this before. If you have a copper coin, and sometimes people have been known to throw copper coins into fountains, does the copper coin explode upon impact? Well, it doesn't, right? That would be pretty wild if it did, but that doesn't happen. In fact, that's one of the reasons why we make coins out of copper, because it's very unreactive. Let's try another example. Let's try sodium plus water. Now we can think of the activity series again, but the fact is there is another little special rule for single replacement reactions that we're going to use in this case. And here's that rule. Group 1 and 2 metals, that is the metals that are found in the first 2 columns on the left side of the periodic table, when added to water, produce a metallic hydroxide and H2 gas. And so, are we going to have a reaction here? Well, yes, we are, because sodium is a metal in group 1. And so one of the products is the metallic hydroxide, so that would be sodium hydroxide, NaOH, and the other product is H2 gas, hydrogen. So this is actually a fairly spectacular reaction. I strongly recommend that you not try this at home because it can be a little bit too spectacular and actually can cause some damage if you're not careful with what you're doing here. Now let's jump right into the next type of reaction, which is double replacement. And just like we said in our previous video about this, in a double replacement reaction, we have 2 ionic compounds that are literally swapping their ion partners here. So in this case, we know that Na, sodium ions, will pair up with bromide ions, and calcium ions are going to pair up with hydroxide ions. Now, if you're unsure as to how these 2 ions are going to pair up, remember that a cation, a positive, is always going to pair up with an anion, which is a negative. So don't try to pair these up, Na pairing up with Ca, because that would be 2 positives getting together. It doesn't work that way. A positive will always get with a negative. So Na is going to pair up with Br to make NaBr, and then calcium is going to pair up with hydroxide to make calcium hydroxide, Ca parentheses OH2. Now, don't forget that you do have to consider the charges whenever you're writing the formulas of these substances. Na and Br have charges that cancel out, +1, -1. Calcium and hydroxide have ion charges that do not cancel out, +2, -1. So that's why we have to have the parentheses and the 2 right there. So that's the rule for double replacement reactions. The ions of 2 ionic compounds will switch partners, forming 2 new ionic compounds. Let's try another example. Here we have silver nitrate being added to aluminum chloride. And once again, the same rule is going to prevail here. In most of these double replacement reactions, the ions of those 2 ionic compounds will switch partners, forming 2 new ionic compounds. So Ag is going to pair up with the chloride ion, AgCl, and those charges cancel out because silver is a +1 and chloride is a -1. Now on the other one, aluminum is going to pair up with nitrate to make aluminum nitrate. And aluminum has a +3 charge, nitrate has a -1 charge, so that's why we have to swap the charges and put the parentheses here. So those are the products for this example here. So once again, we just swap those ions, write the formulas, and write the answers just like we would any ionic compound. Now, let's try another example here. This time we have HBr plus KOH. And in this particular type of double replacement reaction, honestly, we could write it just like the other one. We could take the H and pair that up with OH to make HOH, which actually sounds like H2O, doesn't it? And we could add in K pairing with Br to make KBr. However, this is kind of a special case. In fact, we give this special type of double replacement reaction a name because this is not just any 2 ionic compounds we're adding together. We're adding together an acid and a base. If it starts with hydrogen, we're going to call it an acid. If it ends with hydroxide, we're going to call it a base for this purpose. And the rule here is that an acid and a base react to yield water and another ionic compound called a salt. So H reacting with OH will get you H2O, which is water. And then potassium ions reacting with bromide ions gets you potassium bromide, which is KBr. And this specific type of double replacement reaction is called a neutralization reaction. Now that's a word you've probably heard before. A neutralization reaction is when we take an acid and react it with a base, and they basically just cancel each other out. They literally neutralize each other. And so that's why we call this a neutralization reaction. So that's a good example of this. And yes, that does mean that KBr, potassium bromide, is chemically considered a salt. Most ionic compounds are considered salts. Salt does not just refer to the stuff that you sprinkle on your French fries. That's table salt, sodium chloride, but in chemistry, we have lots of salts that we can work with as well. Now, let's take a look at the fifth type of chemical reaction. This is the combustion process. And the nice thing about combustion is that whenever you have a complete combustion of any hydrocarbon in oxygen, the products are always going to be the same. It's always going to give you carbon dioxide and water. So in this case, we have C4H10 plus O2. Well, it's a complete combustion. So guess what the products are? Carbon dioxide and water. And I suppose we could do the same thing for this. We have octane here, C8H18 plus O2. And so since it's a combustion, guess what the products are going to be? For any complete combustion, it's carbon dioxide and water. So we can write those down. A lot of students tell me that combustion reactions are their favorite type of reactions because the products are very easy to remember, carbon dioxide and water. So I know this video was a little bit longer than some of the others, but I hope you learned something from this. There's a lot going on here. And to get good at predicting products of reactions, you just have to practice. And so if you practice and do more of these, you're going to get better. Hope you learned something from this video. If you did, please slam that thumbs up button. I would really appreciate it. That way, videos like this get out to other great chemistry students just like yourself who are trying to learn. Thanks for watching. I hope to see you in the next video where we can learn some more chemistry together.